So as we discussed in the first session, parameterized problems, so this is a recap. A parameterized problem consists, an instance of a parameterized problem consists of the actual input plus a parameter, and parameter is assumed to be a small value. And what are we looking for? We are looking for an algorithm which we call as an FPT algorithm that will solve the problem exactly in time f of k, which is maybe a polynomial function, but it is independent of n. It depends only on k and polynomial in input size. Okay. So before I go to the next technique, as I have mentioned before, this area of parameterized complexity is fairly young. When I say young, compared to other algorithms for NP-hardness, algorithm for bypassing NP-hardness techniques, like compared to approximation algorithms or randomized algorithms, this was introduced somewhere around in the 70s, so it's like around 35 years old. And maybe I'll just mention some of the textbooks that you can refer for parameterized algorithms or parameterized complexity. First one is Fundamentals of Parameterized Complexity by Downey and Fellows. And another case, by and Grohe. Okay. So these two books, Downey and Fellows actually are the founders of this area. They are the founders of parameterized complexity, and therefore this book, as you expect, it is fairly deep. It explains all the complexity theoretic aspects of it as well. And similarly, parameterized complexity theory by Flum and Grohe, it's also a comprehensive book on parameterized complexity. Whereas this book, An Invitation to Fixed Parameter Algorithms, this is by Rolf Dermer. Okay, so this book is more into, it describes more or it discusses the algorithm design techniques in FPT field. And there is a very recent book called Parameterized Algorithms by it's a group of authors. There are 8 authors. Okay, so this also it's more it gives more stress towards the design aspect of parameterized algorithms. It's also discuss some kind of lower lower bounds to certain extent, but the stress is on again algorithm design. So a fairly new book came in sometime during the last 2 years, 2 to 3 years. Okay, so these are some of the books that you can refer, and to know more about the recent research that is happening in the field of parameterized algorithm, you can, of course, there are papers which are published in leading theoretical computer science conferences and algorithms conferences in general, like TFoCS, SCG and all. In addition, there is a specialized conference, so a workshop on parameterized algorithm and exact computation, IPEC. So this conference exclusively publishes papers on FPT. Okay. So this, you can refer this for further things. Okay. Okay. So this was the definition of parameterized algorithms. And before we go to the next technique, we stopped midway actually last time in between a problem. We are discussing kernelization and we are discussing edge clique cover. I hope you went back and thought about it. So you remember what are the reduction rules that we performed or we used? So, okay, I'll go back. So edge clique cover is given a graph G. You have to cover every edge using k cliques. Okay, so every edge should be in one of the cliques. So you have to select k cliques such that every edge, k cliques which are subgraphs of the graph, such that every edge is in at least one of the cliques. Okay, and the reduction rules we used was, if there is an isolated vertex, we delete it. Of course, it's not going to help us. If there is a isolated edge, then you add it to the solution, because there is only one way to cover an isolated edge. It is to take this as a clique. So you take it and reduce the budget by 1. And the last reduction we performed was this. If there exist two vertices u and v such that their close neighborhoods is the same, then we delete one of them. Okay, so take let's say there exist u and v such that neighborhood of u is same as neighborhood of v, then delete v. Okay, why was this reduction rule okay? Or why was this correct? Right. So to prove that this is what we will say as safe. So when a reduction rule is correct, or it will give you an equivalent instance, we say that the reduction rule is safe. So this reduction rule is safe because, let's say, G is the graph which contains both u and v, and G prime is the graph in which v is deleted. Okay. And what do we have to prove? G is a yes instance if and only if G prime is a yes instance, right? Okay. So how do we prove that? So G has v in it. So yeah. So assume one direction. Right? So assume G has a edge clique cover of size k. Then can you prove that G prime also has an edge clique cover of size k? It is easy to see, right? Because G prime has less vertices. So if there is k cliques covering G, then there are k cliques covering G prime also, all the edges in G prime also. Okay, so G prime is a sub. G prime is obtained by deleting some vertices from G. Okay, so that was the easy part. What about the other direction? Like, assume G prime has a k clique cover. Then how will you prove that G also has a k clique cover? So G prime does not contain V. Okay, so you have to prove that. Okay, so take the clique cover in G prime. Okay, so V is not in this, right? Okay, so we want to extend it to G so that V is, all the edges which contains V is also covered. How can we prove that it is possible? Yes. We'll choose what?
Like one of the cliques G, right?
And
add a vertex to it. That vertex will be B.
No, can we take any clique? Because you take any clique, we should do. I don't think any clique. So we should have edges to that, the vertices in that clique.
Yeah, the condition is that the neighborhood, like they should have the same neighborhood.
Okay, so you're saying one of the cliques where U is present. I'll say all the cliques where U is present. So take the cliques which where U is present in the solution for G prime and add V to those cliques. Okay, we still get a clique because the neighborhood of U and neighborhood of V are same, right? So those edges are there, so we'll still get a clique and we get the clique cover of the same size. We are not adding any new cliques, we are just expanding the cliques which are already there. Okay, so that's why. So therefore this reduction rule is safe. Okay, so we will continue this applying this reduction rule as long as it is possible. Okay, and what we have to prove next? We have to prove that after we run these reduction rules, we have got a new instance which is small. By small I mean one which is bounded by a function of k, right? Okay, so I also gave this hint what that function of k is, 2 to the power k. Okay, so can we prove that after running these reductions, we'll get a kernel of size 2 to the power k? Number of vertices in this reduced instance is only, it's 2 to the power k, if it is a yes instance. Okay. So do you understand the statement? I'll repeat. So after running this, after applying these 3 reduction rules exhaustively, okay, if the remaining vertices, if it is a yes instance, will contain only 2 to the power k vertices, at most 2 to the power k vertices. How will we prove this? No, if there are k cliques, yes instance means there are k number of cliques. We are not saying anything about the size of the clique. There are k cliques, that's it. So each can be like a large clique. But okay. Okay. So if
that is possible, and if I assume that, then one of the reductions is violated.
Okay, so which reduction are we trying to violate?
Either it will be the isolated vertex,
okay,
or it could be the
third one, common neighborhood. Okay, how?
So basically, you can choose more
Okay, right. I'll hear that proof later. Any other thoughts? Yes. Okay.
Then you cannot have two vertices which are a part of the exact same set of features. Because that means they will be either single edge or have the same neighborhood.
Single edge is fine, but they'll have the same neighborhood. Yes.
So now you have k cliques and more two vertices can have the same.
Can be part of the same set of cliques. Yes, right. Okay. So I'll restate that proof again. So we are assuming this is a yes instance. That means there exist k cliques that covers all the edges. Okay. So let's call the cliques as C1, C2 up to some Ck. Okay. So these are the cliques that will cover. Okay. Now we'll consider all the vertices also. So V1, V2 up to, we don't know, some V, what should I call it? I'll say V R. Okay, I want to prove that R is a function. Right. Okay. Now I'll say, I'll do this. So if V1 is part of click C1, let's say I will put a 1 here. Okay, if C1 contains the vertex V1, we'll put a 1 here. Otherwise, if V1, for example, if V1 is not in C2, we'll put a 0 here. We'll do it for every vertex and every click. So for every vertex corresponding to every click, you put a 1 or 0 based on whether the vertex is in the click or not. Okay. So for every vertex, we get a bit string of length k. Right? Okay. Now what he is saying is, for two vertices cannot have the same bit string. Okay, what is the contradiction if two vertices have the same bit string? Have the same bit string means they are contained in the same set of cliques in the solution. What does it mean? Third reduction rule. That means their close neighborhood is the same. Why? They're in the same clique means they have the same set of neighbors. Like we can say it's kind of a subset, like all the neighbors of U are also the neighbors of V, and there cannot be another neighbor which is not in one of these cliques. Why? Because if there is, let's say, like, see, these are all the cliques where V is part of. Let's say U is also here. What are we saying that? So U is also in this clique means, so these are all neighbors of V. They are also neighbors of U, right? And from there, I'm saying that all neighbors of V are also neighbors of U. Why? Because if you cannot have a neighbor outside this clique, because if there is a neighbor like this, who will cover this edge? This edge is not covered. Okay. So since every edge V is contained in is covered, all the neighbors of V should be in one of these cliques. And what are we saying is you also have the same set of neighbors. Then that means reduction rule 3 can still be applied, which contradicts our assumption that we have exhaustively applied that. Okay. So that's what. So for every vertex, the bit string will be different. No two vertices can have the same bit string corresponding to it. How many bit strings of length k can be there? 2 to the power k, right? So therefore the number of vertices cannot be larger than 2 to the power k. So we got a kernel which is of size bounded by a function of k. So this is the kernelization. Okay. So the algorithm goes like this. You apply the reduction rule as long as it is possible, and after that, if you get an instance which is of size greater than 2 to the power k, you say no. If it is less than 2 to the power k, you run a brute force algorithm on it and check whether edge clique cover exists or not. Okay. Questions? Okay. Next. So we have discussed branching algorithm and kernelization, two techniques. Today we will explain a new technique, iterative compression. Okay. So this is generally used for minimization problems. At least I will explain it in terms of generalization, minimization problem. Okay. So iterative compression is this. Given a parameterized solution, let's say, given a parameterized problem, a standard parameterized problem, assume we are looking for a solution of size k. Okay, we are looking for a solution of size k. This is our question. Be it vertex cover, feedback vertex, whatever. We are looking whether there is, we are investigating whether there is a solution of size k. Now let's assume I'll tell you See, I don't know whether there is a solution of size k or not, but I can give you a solution which is slightly larger than k. Okay, so assume I give you a solution of size k plus 1. So what are you looking for? You are looking for a solution of size k, and I am giving you for free a solution of size k plus 1, or even 2k, or let's say some solution, some function of k will do. So it's not exactly what you are looking for, but it is somewhere there, right? It's near to what you are looking for. It's marginally better, it's marginally worse. So what will you do? So as someone who is looking for a solution, and considering the fact that you are looking for a size of solution k, and I am giving you k plus 1, which is only slightly bigger, and the fact that I am giving to you for free, right? We have a tendency to grab anything we get for free, right? So okay, I am giving you k plus 1 free, so you grab it. Okay, so you take k plus 1, but still you haven't answered your question whether there is a solution of size k or not. Okay, right? So what do? So you take the solution with the slightly larger size, or size k plus 1, and so let's call it z. Now you are trying to see, can you compress z so that its size is only k. So this is the essence of iterated compression. Okay, so you start with a solution which is of slightly larger value than what you are looking for, or slightly larger than the budget, and you try to compress this into the size you need. Okay, right. And what usually happens in a compression step is this. So I'll explain it. Hopefully this will be more clear when I give an example. So you have z, and z is not an optimal solution. So you will consider all possibilities in which the optimal solution will intersect with z. Or in other words, from z, you will make a guess how many of the elements in z is actually in the optimal solution. Okay, you make this. When I say guess, I mean you consider all possibilities for it and you branch on it. Okay, you independently compute each of them. Okay, so branch in all ways, an optimal solution x will intersect with z. And now what do you know? Okay, and of course, if the compression step can be performed in FPT time, then the problem is in FPT. We have an FPT algorithm for this, right? Okay, so the idea is this. You are looking for, so let's say this is your problem instance. I have given you a solution which is slightly larger, let's say k plus 1. Okay, so this is not the solution you need, but this is what you have. Okay, now we'll assume, or now we'll guess, or branch on, whatever, on, let's say we have an optimal solution x. We don't have it yet. Let's assume there exists an optimal solution x. Okay, and check how x will intersect with this. So this is our z and this is x. Okay, so maybe this is x. It will have some intersection with z. Can be null also, right? So you will guess what is this intersection. Okay, so what do you know about with respect to z? What do you know, or what is your guess saying? That this is part of the solution that you have guessed. This also tells you that this part of z, the remaining element of z, it's not part of solution. That is the information that you get from this guess. Okay, so what are you looking for now? You are looking for a solution which does not contain this part of z. Okay, and later then you will find some structure in the instance such that Z, this part of Z is not there, and you use that structure to design an algorithm. That is the basic idea. Okay, I'll come back to this to the theory of it later, after we see an example. Hopefully after the example it will be easy. Yes. Okay, right. Okay, so let's go back to our favorite example of vertex cover. So vertex cover, the problem is this: you are given a graph. Yes. Yes, and there's Z. It can be null, right? So that's what you consider all possible intersections of Z with X, and that's where your FPT time comes through. So in how many possible ways X can intersect with Z? Right? Z is of size k plus 1 or 2k or something, right? So the number of subsets of Z is 2 to the power whatever the function of k, it is still a function of k. Okay. And you do a polynomial number of computations on each of them, you are able to. K is the size of the solution you are looking for. K is the budget, let's say. Okay, so now since you are looking for k, you can, when I say optimal solution, I mean k size solution. K is a parameter. Okay, so vertex cover using iterated compression. So what was the first step of iterated compression? Get a solution or size slightly larger than k. Okay, so vertex cover, given a graph G, you are looking for a subset of vertices such that for every edge, at least one of the endpoint is in this subset. That is a vertex cover, and you are looking for a vertex cover of size k. Okay, so you start with a slightly larger solution for vertex cover. Okay, and how do you get that solution? Okay, so let's start with what we know. We know there is a 2 approximation algorithm to vertex cover, right? Right? All of you are aware of that algorithm, right? Okay. So you run this. It's a polynomial time algorithm, right? So you run this polynomial time approximation algorithm, and you get a 2 approximation to the optimal vertex cover. Okay, I'm not saying k. You get an 2 approximation to the optimal vertex cover. Let's call it Z. Okay, and if what is Z contains more than 2k elements, it's a 2 approximation, right? So if Z contains more than 2k elements, that means what does it say about the optimal solution? It is larger than k, right? Because you are running a 2 approximation algorithm, the solution should be within twice the optimal solution, right? So it cannot be more, if Z greater than 2k, then it's a no instance. That means there cannot be a solution of size k or less. Okay. So if Z greater than 2k, say no. Then, okay, right. So now you have a Z which is of size at most 2k. Right. So so you got your first step. You got a solution which is of size 2k. Now what was the second step in iterated compression? Yes. Assuming there is a solution of size k, guess how it intersects with this solution of size 2k, Z. Okay, right. So I'll explain it first. Okay. So this is, let's say this is your graph, and you have Z here, which is of size at most 2k. The next step, you will guess what is the intersection of Z with X, where X is an optimal vertex cover or a vertex cover of size k. Okay. So let's say, I'll make that guess. So I'll say this is X and it intersects Z here. Okay. So I'll call this as, so this is X. So this region I'll call it as exit. Okay. So what do I know? Exit is in the solution. That's my assumption. And why is this true that exit is in the solution? X is the solution, but why should this be the intersection of X and Z?
Because it also comes in X.
No, but I don't know it, but I'm like, yes.
Can X be a subset of the proper?
Yes. X. No, if X is X, can X be a proper subset of? Yes, it is. It is. It can be. Then actually at this point itself you solve it, right? Okay. So you don't know what is exit, what is exit. That is why you are going over all possible values of exit. Okay, and one of them should be the correct answer for X intersection Z, right? Okay. So you are doing this for all possible values of exit. So all possible exit intersection Z intersection, or what you are looking at is all possible subsets of Z. Okay, right. So exit is the intersection of Z and X, and you know that this is part of the solution. Okay, so at this point you can do one thing. You know that this is anyway going to be in the solution. You can just delete this from the graph because you have added it to the solution, and delete it and all its neighbors, whatever, and decrease the budget accordingly. Okay, so you need not consider exit in the latter part of the graph. Okay, so you have taken exit and you have deleted exit and reduced the budget. Now consider this part of Z. Okay, what do you know about this part? It is not in the solution, right? Okay, that is your guess at least. So let's call this part as T. So T is not in the solution. So you are looking for a solution, a vertex cover which does not contain T. Okay. Now what can you say about T? So let's see what are the edges that needs to be covered. Can there be an edge here outside Z and X, outside Z union X? Yes.
When we do the approximation, so that doesn't cover all the solutions, or it should cover all the edges.
It will cover all the edges.
It should be a subset aside it should become a subset of this, right?
You are saying it should always be, no, need not be, right? So you have seen, you can build counter example where what you are taking is not optimal. So it is true for any approximation algorithm. You can have the optimal solution can only intersect with it, can even be disjoint. What we know is we have a solution which is of size bounded by something. That's it. Need not say that it should contain the optimal solution. Right? Okay. Okay. So let's see what are the edges that needs to be covered. So all the edges which involves XZ are covered because we have already taken XZ to it. What about edges like this? Can there be an edge like this? Outside Z and X. Outside Z, let's say. Because we don't know X, huh? One of the endpoints? Yes, because we know that Z is a vertex cover, right? If there is an edge like this, who is covering this in Z? Okay, so all the edges are covered by Z, so there cannot be an edge like this. Okay, so we cannot have an edge like this. And what can we have an edge like this inside T? Okay, yes. Because yes, if there is an edge like this, again who is covering it, right? Okay, so this is not in the solution. That is our assumption. Therefore, we cannot have an edge like this also. So it seems that the only type of edges are these, right? Uncovered edges which have one endpoint in T, one endpoint outside T. Edge, which one? Here. Because we have assumed that this is not in the solution, right? Okay, if there is an edge here, can we have a solution which will delete all, like which will not contain any of this? No? Oh, no, that is possible. We can have one in except. I'm saying entirely within T. So we forget about XZ and whatever edges that it covers. Okay. So what I'm saying, so what is T? T is Z minus XZ. So T is not in the solution. So we cannot have an edge here. Who will cover it? Not clear? No? See, what is our assumption? Our assumption is this part T is not in the solution, right? So if you have an edge such that both its endpoints are in T, it cannot be covered in the solution, right? Because you have to choose at least one of its endpoint, but both its endpoints are in T, but we cannot take any vertex from T, right? Okay. All the
are also not going to be saying that this X is in T. When you're talking about those two endpoints, so all the actions are connected to those two endpoints. Those will also be
that there cannot be an edge like that. That's what I'm saying. So you take two vertices in T, they cannot have an edge between them, right? Okay. Or we can say, or otherwise we can say that we cannot have a solution which does not contain T if such an edge exists. Okay. T to XZ. We don't know X actually, right? We are just guessing XZ. So yeah, it can be. This edge is, so you can have an edge like this. Yes, these kind of edges. There. It can be covered by something here, right? Oh, okay, so we don't know X, right? So, okay. Let's say, okay, I will draw it like this. I got your point. Okay. So, see, what we are guessing is just X intersection Z. So, let's say, can even forget about how X looks like because we don't know anything about it. Okay? Right. Okay. So, is it clear that there cannot be edges like this or like this? There cannot be edges like this because it contradicts that Z is a vertex cover. Okay. If there are edges like this, that means our guess of XZ is wrong, and then we say no and go to the next value of XZ. Okay, right. So what the only possible type of edges are this, with one endpoint in T and the other endpoint outside Z. Okay, and how can we cover those edges? Those edges. There is only one way to cover such an edge, right? One endpoint in T we cannot take because that we know that they are not in the vertex cover. Okay, so we have to take this. That's it. So that's what we are going to do. So we will take once for every guess exit, we'll take T and all the edges which goes from T to outside, and we'll take all of them in the vertex cover. Okay, and if it is well within our budget, if it is less than k, we got our k-sized optimal solution. If for none of these values of xz we will get a k-sized solution, that means it is a no instance. Okay. So let x be a solution of size k. So we don't know x yet. So we are assuming that such a solution exists. Then we'll assume or we'll guess the intersection of z with that optimum solution, and we'll branch on all possible values of xz. Actually, we are guessing it. Okay, we'll take every possible subset of z and we'll run the rest of the algorithm for it. Okay, right? And what is? Okay, let w is z minus xz. I've called it t here. So it's w is z minus xz, and what do we know about w? None of the vertices in w are in the solution. So we are looking for a solution which does not contain w. Okay, and so there cannot be an edge in G of w. You cannot have an edge just within w, because then it's a wrong guess. And what? So then what you have to do? We have already added xz to the solution. Now you take all the neighbors of w, neighbors of vertices in w. Okay, all of them should be in a vertex cover, and if the number of such vertices is less than or equal to k, say yes. Otherwise, go to the next value of xz and continue. At the end of all possible values of xz, you still didn't get a solution, then it is a no instance. Clear? Questions? Yes. Then we take the next value of xz and.
But in that we already have xz as one. What is the x we started?
No. So this is xz. Xz is actually every element in the power set of z. We don't know x, right? If you know x, we don't have to run the algorithm at all, right? So we are guessing what is x intersection z. We only have z. We don't have x. So we'll assume first. Let's say first we assume that it is null set. Okay, then we solve it, and if it doesn't work out, you go to the next subset of z, and then you repeat it for all subset of z. You don't know x. It is just if such an x exists, it will intersect z in some way, right? We are guessing that intersection. When I say guess, I mean we are iterating over all possible intersections. Yes.
NW stands for number of vertices
No,
in W.
neighborhood of W. For every vertex, what are the neighbors? The set containing all the neighbors of. Yes.
That means one in inside and other outside the right bucket. So actually, how is the existential union in of W less than k? How it can be less than k?
No, if it is this is a vertex cover, right? This will be a vertex cover. If the size is less than or equal to k, we got a vertex cover of size less than or equal to k. Then say yes. Otherwise, what does it mean? This is not a correct guess.
No, my doubt was that is whether it is equal to k.
It can be. Yes.
So it can be less than k also.
Right. Trivially, right? So if you are looking for even if the optimal is less than k, we have a vertex cover of size exactly k also. Or you can even define the question like that. That's right. Okay. Right. So this was easier because it was easy to find the connection, or it easy to find some property between W and rest of the graph. Okay. So what will be the running time of this algorithm? So all this work after you find xz, these are all polynomial times. Okay, and so it will depend on how many values of xz are there. What are the values of xz? Yeah, it's all subsets of Z. So 2 to the power 2k. So what is we started with a Z or size 2k. Therefore, the algorithm runs in 4 to the power k time. Actually, this can be improved. Here, this worked because we started with a solution of size 2k. Assume we started with a solution of size k plus 1. The running time will be 2 power k. Right? 2 power k plus 1 to be exact. Okay? Right. So, but how do we get a solution of size k plus 1? How can we get a solution of size k plus 1? So you cannot have a better, so I see, I'm sure Professor Murli will cover at some point, vertex cover has an inapproximability result also. We cannot look at, and an additive approximation is too ambitious, I'll say, k plus 1. Remaining vertices were? XZ union? No. See, the running time is because of the number values XZ can take. XZ is all possible subsets of Z, and Z is 2k, therefore all possible subset of Z is 2 power 2k, which is 4 power k. So my question is, can we reduce the size of Z to k plus 1 or k plus 2 or whatever?
This problem we know that the 2k like which we have, the optimal solution will be from that section.
No, it can be disjoint also. That's why I said all possible subsets. You even take null set. This doesn't say that X should intersect with Z. Like X intersection Z can be a null set also, and we are iterating over that also. Was that your question?
The greedy algorithm which we use, right, for day. I mean, the problem was that we could have reduced our constant if they only chosen one vertex, the code did not know which vertex to choose. That's why we take both the vertices. But what I'm trying to say is that maybe the optimal is only out of the
okay.
We start with placing some Z.
Okay.
And if we run this and get it within K, then we are fine. If not, we can remove all of K.
So you're looking at a minimal vertex, or you might not get it also, right? The question is, how do you get? So you start with a Z and you delete all the unnecessary vertices? No.
Randomly give K plus 1.
Oh, okay.
And I do the same procedure. If from K plus 1 I am able to get a K within our budget, then I am done.
Right.
If not, I know that none of them were, because the intersection was not for all the cases, so I don't even need to consider them. I can remove all of them.
But you strongly use the fact that what you start with is a vertex cover. Without that property, this algorithm will not go through. You cannot take any k plus 1 and use this.
Everything, once we get the set is, like, we can keep deleting the vertices which have an edge, and they both are rejected.
We start with a Z.
Yeah, which has 2k elements.
Okay.
And then, like, we see if those elements are, like, connected by an edge.
Okay.
So, like, somehow we are able to delete few of the elements.
No. Even that is, like, what you're saying is that if two vertices are covering the same set of edges, you delete one vertex. But such two vertices may not be there. You can find a minimal vertex cover. By minimal, I mean one cannot be deleted. Like no vertex can be deleted without conflicting the vertex covering property.
Like
But
it will be less than equal to 2k.
but no bound on that, right? It can be still 2k. So it's not clear, and it's not easy to find out a approximation algorithm for the full instance, for the instance of size n. But can we start with a part of the instance and find a k plus 1 sized vertex cover for that and then proceed? For example, what can you think of, can you think of a small part of the subset which can be covered using k plus 1 vertices? You have n vertices in the graph. Okay, so let's start by, okay, I'm not looking at the entire graph. I'll look at a small part of it. Okay, and I'll see whether this has a k plus 1 sized vertex cover. This can be done, right? Trivially, I'll just take k plus 1 vertices of it, and you get a k plus 1 sized vertex cover for it. You take everything, it is a vertex cover. So I'm not looking at the entire graph, I am only looking at the graph or the subgraph on some k plus 1 vertices on it. Okay, so many of the edges I'm not even seeing now. Okay, but you have a k plus 1 sized vertex cover for this subgraph, right? You take each of them, and you trivially get a k plus 1 sized vertex cover, right? Okay, so this is where the iterated part comes. Okay, so what I'll do is, we have seen compression. So this is my graph. Okay, I don't know how to get a k plus 1 sized vertex cover for this, but I'll take only a part of the graph. Okay, so this contains only k plus 1 vertices, and for this, if I can take all the vertices, that is a vertex cover for this part of the graph. So it's not covering edges here, may not cover edges here, but it will cover all the edges here, right? Now what I do is, for this subgraph, what do I know? For this subgraph, there is a vertex cover of size k plus 1. Now I use the previous algorithm to compress that k plus 1 sized vertex cover to k sized vertex cover. It's the same algorithm as before. Okay, so if end of it, if there is a solution, what I'll get? I'll get a k sized vertex cover for this small subset. Okay, right. Now what I will do is, I'll add one more vertex to it. I'll slightly expand this graph, right? So for all the vertices here, all the edges involving vertices here, I already got a k sized vertex cover. I've added one more one more vertex, right? Now I will add this vertex to this k. So what do I get? For this slightly larger subgraph, I have a k plus 1 sized vertex cover. I'll call the compression algorithm again, and I compress it to k, right? It will be possible if the entire graph has a k sized vertex cover. If the whole graph has a k sized vertex cover, a small part of it will always have a k sized vertex cover, right? So I compress it and I get a k sized vertex cover for this graph. Okay, now I'll add one more vertex to this graph and I get a slightly larger graph, and you see where I am going, right? So I have a k size solution for this part, and I'll add this vertex to it. Again I get a k plus 1 sized vertex cover for this subgraph. I compress it, again get a k sized vertex cover, and repeat till I cover every vertex. Okay, so the previous algorithm will work for any z, right?
So, but if the budget is more than k, then we say it will grab and
Yes.
If it is not for the subgraph, then it is not.
Yes, obviously if the subgraph cannot have a vertex cover size k, the whole graph cannot have a vertex cover size k, right? So that's what we are using. Okay. Okay. So this is what I'm doing. So I start with, let's just start with just k plus 1 vertices. Find, you'll take all the vertices as the k plus 1 as the z for it. Do the run the compression algorithm for it, and compress that k plus 1 to k. Okay. Now add one more vertex to it, add that vertex to this K, again I get a K plus 1 sized vertex cover and compress, repeat. So it's just you take one vertex at a time, add that vertex to the graph, add that vertex to the already proved vertex cover, already computed vertex cover, compress it, repeat. Okay. What happened to the running time now? So your running compression algorithm whose running time is now 2 power k plus 1. How many times are you running it? N times. You are doing it for, you are adding one vertex at a time. No. So you are taking the same compression algorithm and you are running it for when you add each of the vertex. So n vertices are there, you are running it n times. Actually n minus k you can say. Okay, right. So the running time has increased, but only a polynomial time. Okay, so the running time is now 2 to the power k. Okay, fine. Right. Okay. Okay, so that's how. Okay. So that's how an iterated compression algorithm usually works. You start with a small subset and kind of repeat it and keep on incrementally increase the input size and run the compression algorithm for each of these iterations. Okay. So let's see one more example. Road cycle transfers. Okay, so just to repeat what we did in vertex cover, you start with a small size solution, then take every possible subset of this small size solution and assume that the rest of it is not going to be in your solution. Find a solution which is disjoint from the discarded one. That's it. Okay, so next problem is odd cycle transversal. So what is the odd cycle transversal is this. Given a graph, for every odd cycle, from every odd cycle means a cycle of length or like a C3, C5, C7, etc. From every odd cycle, delete at least one vertex. Okay, so you delete some vertices such that the resulting graph does not have a odd cycle. What is that graph? So bipartite graph. A graph which has no odd cycle is bipartite. Okay. So this is the problem. Given a graph, X subset of V is an odd cycle transversal for G if G minus X is bipartite. So you remove the vertices X from it, you get a bipartite graph. Okay, and the parameterized problem is this. Given an undirected graph, does G have an odd cycle transversal of size k and parameter is k. We'll try to use iterated compression for this. Okay, so how will iterated compression work? We'll start with the odd cycle or OCT of size k plus 1. We know how to get it, right? You start with a small instance and keep on compressing it till it works for the large instance. Okay, right. So let's assume we are working with a instance of size n, and we got a odd cycle OCT of size k plus 1 for it. Now we want to compress it to size k. Okay. Okay. So as always, what's the first step? You have a solution, let's call it W. Then guess the intersection of the optimal solution with W. Okay. Or in other words, you take every possible subset of W and iterate over all subsets. Okay. Optimal solution is an OCT of size k. What is X? No, you are checking whether there is an OCT of size k. Okay. Now assume such an OCT is there. Let's call it X. No, odd cycle transversal is in the graph. That means one whose removal will make the graph bipartite. Okay, maybe I'll give an example of. So let's say you have a graph like this. Okay, so this has a number of odd cycles, right? So there is a C3, 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 there is a C5, maybe you have a C7, C7 also. Okay, so you want to delete some vertices such that the remaining graph does not contain any odd cycle. So here, I don't know what will be, you take this, let's say you delete this. Is it good enough? Do I have to remove anything else? So if I delete this, I have deleted this edge, this edge, this edge, etc. What I get is, yeah, it has no. Okay, so if I delete all this vertex, the graph is this. It is a bipartite graph. Doesn't contain any odd cycle. Clear? Okay. So this is what you know. So we are looking for. So we deleted one vertex, right? So that vertex is our odd cycle OCT. Okay. The size of OCT in this case is 1. Number of vertices you deleted. Okay. So the question is, does there exist an OCT of size k? Okay. Okay. So it's clear to all of you that if the graph contains only k plus 1 vertices, you trivially get an OCT of size k plus 1, right? You take all the vertices, you delete everything, you get is an empty graph. Obviously, it does not contain any odd cycles. Okay. Okay. So let's. Okay. So you have a graph and you have an OCT of size k plus 1. Let's call it W. Okay. Now, if there is an optimal solution, when I say optimal solution, I mean a OCT of size k. If there is an OCT of size k, we are guessing how this, let's call it X, the optimal solution X, how X will intersect with W. Okay, so, or in other words, how many vertices of W are in X also. Okay, so we don't know it. So what do? We iterate over all possible values of this intersection. Okay. So let's. So that's what I said. Guess the intersection of the optimal solution X with W. Okay. Now we'll call this guess as XW. So XW is the elements which are in W as well as X. So we have in other words, we have taken XW to our solution. Okay. And let T be the rest of the graph. Okay, I meant probably I meant W minus XW. Okay, let's see. Okay, so I think it's a typo. It's not V of G, it is W. Okay, right. And then we delete XW from the graph because you see you have already decided that XW is in the solution. So you decrease your budget by the size of XW and delete the edges which is already taken care of by XW. Started with the solution W which was an OCT, okay, and let's say this is rest of the graph. Let's call this G itself, or let's call it G prime. Okay, so the entire thing was G. W was an OCT of size K plus 1, and G prime is G minus W. What do you know about G prime? W is an OCT, so what do you know about G prime? This is bipartite, right? Okay. Now you assume you take some part of it, okay, and this you have decided it's going to be in your solution. Okay. So what you do is you delete this, and whatever part of G prime which is connected to this, that also you delete, because you have taken it to your budget, right? And you decrease the budget accordingly. Like let's say if this is K prime, then the new K is K minus K prime. Okay. So you have deleted this part. No, this is the size of XW, the one you have taken. You have already taken K prime elements too. So you can take only K minus K prime more, right? Okay. So you have only this now. Let's call this some T or something. Okay. Okay. So now you are looking for a solution of an OCT for G prime which does not contain any vertex from T, right? So the question is whether such a solution exists or not. Okay. So your assumption is that T cannot contain any, or T cannot intersect with the solution. That means, or for it to be true, you have for it to be true, it should be the case that this is already bipartite, T is bipartite. What if T is not bipartite? T contains an odd cycle. If you want to kill that cycle, you have to take a vertex from T itself, some vertex from T, which is not possible, right? So you can assume that this is also bipartite. Otherwise, you can stop the algorithm and go to the next iteration. Okay. So what do you know now? So you have so you have T and you have G prime. Both of them are bipartite. Okay. Now the question is, can you delete some vertices from G prime so that the whole thing G prime union T is bipartite? Okay, right. So let's see. So T, we cannot touch T, right? It's not going to be in the solution. So let's say, and we know that T is bipartite. That means we can we can partition T into two sets like this, such that all the edges go from definition of bipartite. Or in other words, let's say you can color this graph using two colors. That is the same, that's equivalent definition of bipartite graph, right? So let's say I color and 2. Okay. So actually there is no unique way of, there may not be a unique way of coloring a graph using two colors. There may be many possible ways in which T can be two colored. Okay. So what are we doing here is, we will fix a particular coloring for T. Okay, the idea is this. So we'll give a coloring to T as some vertices get color 1, some vertices and color 2. Then we'll try to extend it to G prime. What do we mean by extend a coloring? extended partial coloring?
We can give the same.
Yes. So you color some part of the graph and you color the remaining part of the graph so that the first colors you give, it stays as it is, and other vertices are colored such that this is not disturbed. Okay. So all of you know what is proper coloring and all, right? Okay. So proper coloring means for an edge, its endpoint should get different colors. Okay. So let's say this is a proper coloring 40. Well, this is a fixed proper coloring 40. Okay. So we don't know whether this is the actual coloring we have to look at. So what do? Iterate over all possible colorings of T, right? Right. Okay. So you iterate over all possible 2 colorings of T. Okay. Now take one such coloring. So this has color 1 and this has color 2. Now G prime is also bipartite. Okay. That means you can 2 color G prime also using 2 colors, right? So this has color 1, this has color 2. And all the edges here, they are proper colored. And all the edges here, they are also proper colored. But is the entire graph proper colored?
So like we'll check from a particular set of G, if it has edges 1 and 2, both sides.
Here and
Yeah, so it will be a part of
OCT. We don't know yet, right? So we can even recolor. See, this only we are considering all colorings. Here we are just starting with a coloring. So.
Yeah, but like if it has edges in both of the sets,
then
it's
if it has endpoints in both the sets.
Yeah, then it's an odd set.
Okay, that's what. So we need. It might not be a consistent or proper coloring. That's your point is. Okay. So here, we have taken this 2 coloring of T and a 2 coloring of G prime, and the edges going from here to here and here to here, they are proper colored, right? That's how we colored them. But in the full graph, there may be edges going from here to here. It is possible, right? Because we haven't considered these edges because it is T. We have taken T and G prime separately. So we have color 1 here, and the other endpoint is also color 1, right? Okay. So what can we do about that edge? We cannot do anything here. Okay. So whatever we have to change here. Okay. So you have to pick this to the OCT, or you can delete this also. Right? Right. Okay. When you say pick, you mean delete. Okay. So you you can pick this into OCT, or that means you can delete it, or you can change its color also. Recolor it as to 2. Fine.
Provided it doesn't share an edge in the set.
In the
Set in G prime.
here. Okay. So that's what. So when we recolor, there might be a conflict, right? So we want to. So this is what's going to happen in G prime. You take the edges, or you take the vertices which are in conflict with T. We know that to solve this conflict, you can either recolor it or delete it, but you don't know what to do, right? So maybe you recolor something instead of deleting it. Might not give you the correct solution. Right? So here is where we are trying to find more structure into this. Right? So let's look at the vertices here. What are the conflicts that can happen, or what are the type of edges that can come from T to G prime? First is the edges going from 1 to 1. Okay, so let's call these edges. So how can you handle these vertices? Either you can change their color, or you can delete it. Okay, so let's take all the elements here, all the vertices here whose color needs to be changed or deleted. One of the matrices. So let's call it the set C. Let's add it to set C. Okay. Now, what about the vertices which have edges from here to 2? What can we say about them? Suppose there is an edge from here to here. They are okay and you cannot change their color. Yes, if we change, if we change, it will conflict with this coloring, right? So these are the ones that should retain their color. They can be deleted also. Okay, so let's call those vertices R. Let's add them to the set R. Okay. So we got a C and R, and similarly this side also you will get such things, right? So the edges, if there are edges from 2 to 2, again they needs to be recolored. They need to be recolored or deleted. So we'll call them C itself. And if there is edges from 1 to this 2, they need to retain their color, or they can even be deleted. Okay. So we got two sets. So we have a set of colors, let's call it C, which can be deleted or recolored. We have another set R, which are the vertices that can be deleted or their color should be retained, should not be recolored. Okay, so we'll consider these sets. Will it be always disjoint? Not necessary, right? So what can we do about vertices which are in the intersection of C and R? Delete it. There is no other way. Okay? There is no way a vertex can be recolored and retain its color. Only one of them can happen, right? So they can delete. It will be deleted. So we have like vertices like this and edges going over them. So we want to find a subset of these vertices such that this is like, the ones that needs to be recolored or deleted are recolored or deleted, and the one needs to be retain their color or retain their color, are retaining their color or deleted. So we have to choose the deletions like that. Okay. So there is this property that okay. So there are some edges here. There is some vertices here that needs to be deleted. And what can we say about those edges or those vertices is this. Okay. Suppose after you delete some vertex, suppose you found an OCT and all, right? So you take the resultant graph. Okay. Now suppose you take a vertex which is in C and you take a vertex which is in set R. Okay. So this is after deleting. Okay. We don't know what to do, so we are trying to find out. So you take a vertex in C and a vertex in R. Okay. Now assume that they have a path. Okay. They have a path in the resultant graph. So what do we know about this vertex? We know that its color needs to be changed. Okay. So for this edge, this color will change. See, we started with a proper coloring. Okay. So what about this edge? Oh, sorry, this vertex then. If you change the color of this, what can you say about the color of this? That needs to be changed, right? So that means this also should be a C vertex. Okay. Now, if this is a C vertex, what is this? This is also a C vertex, right? So, is there any way like, what happens when you reach here? It should also be a C vertex, but it's an R vertex. Contradiction. right? So what did we just prove? Prove that we should delete the vertices such that there is no path between a C vertex and a R vertex. Okay? In other words, you have two sets and you have to find some vertices such that there is no edge between, if you delete these vertices, there is no edge between C and R. Okay? All the paths should be like go between them. Okay? So this is called a separator or of a graph. It's kind of a vertex analogy of, you have seen it in an algorithm class. The edge analogy of this. Like you want to find a set of edges such that two sets are separated. What is that called? Cut. Okay. So you are actually finding a cut of minimum size. That will give you your OCT. So if you delete that cut, all these paths are gone, and what you get is a bipartite graph or two-colored graph which extends this coloring. And how much time it will take to get a mean cut? Polynomial, right? Can use TFoCS or right? So, okay. So that's algorithm. So once you have you fix a coloring, you fix a two coloring for T, then start with any coloring of G prime and define C, and actually C and R, it doesn't need a coloring also, let's say. Okay, so you get these two sets C and R, find a mean cut between C and R, that will be the OCT. And if that OCT is of size K, good, you got your solution. Otherwise, what do you do? Go back, check, try some other coloring, and again repeat. Okay. So just to recap, what did we do? We started with a solution W of size K plus 1. First, guess the intersection of the solution with W, and you get a T. Then what is the next step? You guess a two coloring of T, and then run a mean cut algorithm. Okay. So what is the running time for this? Okay, I haven't. Such that, okay, that can be extended to be. Guess this coloring on 2 power k time. Yeah. So what is the running time for this? How many guesses you made? First, you guessed a subset of W was of size K plus 1, and for that guess, you guessed a two coloring. Right? So, how many two colorings are there for a set of size I? Let's say I. Two colorings. In how many ways can you color a set of size I using two colors? 2 power I, right? Okay. So for each subset of size I, you have 2 power I. And how many subset of size I are there? So you are starting with k plus 1, and so k plus 1 choose I, and this goes from 0 to k plus 1. So this is the total running time. I0 to k plus 1 choose I, 2 power I. This is, you can prove that this is 3 power k plus 1 maybe. Okay. Questions? Okay, so this is a slightly non-trivial algorithm because you had to it was not, the property was, or the structure was not easy to see as the vertex cover, but okay. So you got an OCT algorithm which runs in 3 power k time. So that is iterative compression, and given questions like this, I decided to go green and not print papers. So just try this. The first question is on 3 hitting set problem. You have seen hitting set problem in approximation algorithms, right? So 3 hitting set problem is again a hitting set problem, but all the family is of size 3. Okay, you want to find a heating set of size k, right? And use iterative compression. Okay, here the idea is you can see how, or remember how iterated compression works, and at some point you can reduce it to a vertex cover problem, and then you solve the vertex cover. The second is FPT algorithm for cluster vertex deletion problem. It was cluster vertex deletion problem was there in the first problem sheet, right? And I've already given the structure. So if the graph is a cluster graph, if there is no P3 in it, so you have to use that and try to. We'll discuss the solutions for these problems on Friday. So next class we'll see lower bounds like the hardness, how to prove a problem is W hard, and then we will discuss the problems. Okay.